I'm going to get started. So, chapter 2.2, the homework, the second homework for chapter 2, named Chris. So the homework for second homework for chapter 2 is due tonight. The first homework for chapter 3 is due on the 25th. The second homework for chapter 3 is due on the 11th of March because of spring break. The chapter 2 quiz will be today. And then the exam on chapters 1 and 2 is on Monday. So the exam will be in lecture from 1 to 2:15. There is a lab scheduled, but we will not be doing a lab unless you have a lab you need to make up. You can do makeups then. Much like quizzes, you get one sheet of notes for reference, and a calculator will be required. So let's do a quick review of Newton's first law. An object will remain in motion, will remain at rest or in uniform motion in a straight line unless it's acted on by some external unbalanced force. And balanced forces have equal magnitude in opposite directions. And an external force is a force applied to the entire object or system. So here's an example of a problem. A 10-kilogram drone moving 4 meters per second to the east has a downwards force from gravity of 98 newtons and an upward force from its propellers of 98 newtons. Those are the only forces on this drone. After 30 seconds have passed, what's its velocity? Given that these are the only forces on the drone, and it started moving 4 meters per second to the east. So, total force here is 0. 98 newtons up, 98 newtons down. They cancel out. So, the velocity will be constant, 4 meters per second to the east. Let's go over Newton's second law. Force equals mass times acceleration, where force is the net force, the unbalanced force, which is likely the vector sum of 2 or more forces. Mass and acceleration are concerning the whole system. And the units of force are newtons, which are kilogram meters per second squared. So here, if you have a penny and a feather that fall at the same rate in an evacuated tube, the penny has a mass of 2.5 grams and the feather has a mass of 0.025 grams. The acceleration of gravity is 9.8 meters per second squared. What is the force on the penny and what is the force on the feather? We'll give you a minute or so to work on this. This will require converting to kilograms. Remember that there are 1,000 grams in a kilogram. So our first step will be to convert the masses to kilograms. We're going to be using force equals mass times acceleration. We know the acceleration, it's 9.8 meters per second squared. We know the masses of each object, but we need to convert those to kilograms. So the weight for this force from gravity is mass times g. So the weight of the penny is the mass of the penny times g. 2.5 grams is 0.0025 kilograms. And 0.025 grams is 0.00025 kilograms, or 2.5 times 10 to the minus 5 kilograms. So the weight of the penny is 0.0025 kilograms times 9.8 meters per second squared, which is 0.0245 newtons. Which rounds to 0.025 newtons to 3 significant kilograms. And the weight of the feather is 2.5 times 10 to the minus 5 kilograms times 9.8 meters per second squared, which is 2.45 times 10 to the minus 4 newtons, which rounds to 2.5 times 10 to the minus 4 newtons, because this is 2 significant figures. Yes. Why do we have to do it? Because newtons are kilogram meters per second squared. If you didn't convert, both of these numbers would be 1,000 times bigger and would be wrong. So basically, because of the way we've defined this equation, it assumes that mass is in kilograms and acceleration is in meters per second squared, then force will be in newtons. There is another system that uses grams, but then you'd have to do acceleration in centimeters per second squared. So you'd have to convert that, and it would have a different name that I don't remember off the top of my head, so I don't want to use it. But because the base unit is kilograms, you have to convert to kilograms for it to be the right number of newtons. So if you have a 3,000 kilogram car that experiences a net force of 90,000 newtons, what will its acceleration be? So here, force equals mass times acceleration. So acceleration is force over mass, 90,000 newtons divided by 3,000 kilograms gives us 30 meters per second squared. And just a quick overview of Newton's third law: for every action, there's an equal and opposite reaction. If you push on something, it will push back on you with an equal and opposite force. So the force of 1 on 2 is minus the force of 2 on 1. So that was a quick review of what we've covered so far. Let's move on to Newton's law of gravitation. Gravity is one of the 4 fundamental forces of nature. These are gravity, the electromagnetic force, the strong nuclear force, and the weak nuclear force. It is the weakest of the 4 fundamental forces of nature. But in your day-to-day life, the only fundamental forces of nature you really interact with are gravity and the electromagnetic force. Every everyday force you encounter is fundamentally electromagnetic, except for gravity. So we don't really know what causes gravity. We can only really describe it. And Newton's law of universal gravitation describes gravity under most circumstances. Technically, to be fully accurate, you have to expand on this and go into general relativity, which we will definitely not do in this class. But Newton's law of universal gravitation says every particle in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. So that equation, this is entirely dead. Let me grab a different one. Force of gravity, let me make it with a big G, is big G. Notice that is a capital G, not a lowercase g, where big G is the universal gravitational constant, which is 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. Times mass 1 times mass 2 over the distance between the masses squared. So that's the universal form of gravity. G here at 6.67 times 10 to the minus 11 is a very small quantity. It's thought to be the same throughout the entire universe. It was first measured by Cavendish 70 years after Newton's death. And it is not a force, and it is not equal to little g. Big G and little g are different constants. Big G is universal. It is the fundamental constant for the strength of the force of gravity. Little g is just how strong the acceleration of gravity is on Earth at the surface. So, you know, you can write an equation for little g that uses big G. So the forces that attract particles together, they obey Newton's third law. They come in pairs. They're equal and opposite to each other. So force 1 equals minus force 2, or mass 1 times acceleration 1 equals minus mass 2 times acceleration 2. But if the two objects have very different masses, like we experience day to day, the acceleration of this pen is much bigger than the acceleration of the Earth. And for a sphere, you know, for a ball that is homogeneous, so for a homogeneous sphere, or it's a little better than that. You can actually, it works for any sphere that has the right kind of symmetry. But for a homogeneous sphere, the gravitational force acts as if all the mass of the sphere were at the center. There's some you can do some math to show that that's the case. I'm not going to because it requires calculus name. But it is possible to show that for a homogeneous sphere, the gravitational force will act as if all the mass of the sphere were exactly at the center. And so you can do the mass force of gravity on Earth by basically just plugging in the mass of the Earth and the radius of the Earth here, and this will be the mass of the object. And so you can get little g from that. So here we have two objects. One is a mass of 1 kilogram, the other has a mass of 2 kilograms, and they're 1 meter apart. So what's the magnitude of the gravitational force between these masses? And you'll see why it took 70 years after Newton died to actually measure big G. It's because this force is extremely weak. So force is big G times mass 1 times mass 2 over the distance between the two masses squared. So 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared times 1 kilogram times 2 kilograms divided by 1 meter squared. That is just 6.67 times 10 to the minus 11 times 2, which is 1.3 times 10 to the minus 10 newtons. It's a tiny, tiny, tiny force. And, you know, and if you compare it to, it's less than a billionth of the force that the Earth is pulling on those objects. Now, if we look at the force of gravity on Earth, we can plug in the mass of the Earth and the radius of the Earth, because Earth is a ball or close enough to a sphere. So we can say that the gravity is just as if all the mass was in the center of the Earth. So it's the mass of the Earth and the radius of the Earth. And this force, big G times the mass of the object times mass of the Earth over radius of the Earth squared, is just the object's weight, which we know is mass times little g. Weight is mass times little g, but it's also equal to big G times mass of the object times mass of the Earth over radius of the Earth squared. So the mass of the object will cancel out, and we'll find that little g is big G times mass of the Earth over the radius of the Earth squared. So that's how you can calculate little g for some arbitrary for Earth, just from the fundamental constant and the equation for universal gravitation. Now, weightlessness in space, as you see here, is not actually a result of there being no force of gravity. In fact, this person at the International Space Station is accelerating towards the Earth. Let me look it up. At about 8.6 meters per second squared. The thing is, so is the space station. So this is like if you're in an elevator and you and the elevator are falling at the same acceleration. Compared to the elevator, you're weightless. And because it's orbiting around the Earth, it's constantly missing the ground. And so it stays orbiting the Earth. The trick to orbit is to travel sideways fast enough that you miss the ground as you fall. So weightlessness in space is just the result of both the astronaut and the spacecraft falling to Earth at the same rate. So you can experience weightlessness for a short time by, plummeting or going on a drop ride in an amusement park. So let's find the gravitational force between 1 times 10 to the 6 kilogram, million kilogram, or 1,000-ton masses at a distance of 10 meters. So much bigger masses. So remember, force of gravity is big G, 6.67 times 10 to the minus 11, times mass 1 times mass 2, divided by the distance between the masses squared. So force of gravity is big G times mass 1 times mass 2 over the distance between them squared. So that's 6.67 times 10 to the minus 11 times 1 times 10 to the 6 kilograms times 1 times 10 to the 6 kilograms divided by 10 meters squared. So that's 6.67 times 10 to the minus 1 newtons, or 0.667 newtons. You're 10 to the minus 11 times 10 to the 12 divided by 10 to the 2. So here's an actual calculation of the force of gravity. The moon has a mass of 7.35 times 10 to the 22 kilograms. The Earth has a mass of 5.97 times 10 to the 24 kilograms. And they're separated by a distance of 3.84 times 10 to the 8 meters. So what's the force on the moon from the Earth? So again, this is fairly straightforward. Just plug in the numbers. Force of gravity is big G times mass of the moon times mass of the Earth over the distance between them squared. So 6.67 times 10 to the minus 11 times 7.35 times 10 to the 22 times 5.97 times 10 to the 24 divided by 3.84 times 10 to the 8 meters quantity squared, which comes out to 1.98 times 10 to the 20. So 1.98 times 10 to the 20 newtons is the force on the moon from the Earth. And the acceleration of the moon from the Earth caused by the Earth, you can find by dividing by the mass of the moon. And that's like 2.7 times 10 to the minus 3 meters per second squared. 0.0027 meters per second squared. So here, knowing that G is big G times mass of the Earth over radius of the Earth squared. If a planet has half the radius of the Earth and 1/8 of the mass of the Earth, what will the acceleration on gravity be, due to gravity, be on the surface of the planet? So you could plug in the numbers for the mass of the Earth and the radius of the Earth, but you can also do this by just comparing G on Earth. So the way you can do this, G on Earth is big G times mass of the Earth over radius of the Earth squared. G on this planet is going to be big G times 1/8 the mass of the Earth, because the mass is 1/8 the mass of Earth, divided by 1/2 the radius of the Earth squared. This will come out to 1/8 big G times mass of the Earth over 1/4 radius of the Earth, which simplifies to 1/2 big G times mass of the Earth over radius of the Earth squared. So 1/2 of G on Earth. Because this is the same as this. So that would be 4.9 meters per second squared. Be half of G on Earth. So here, if a planet has 3 times the radius of the Earth and the same acceleration due to gravity, what's the mass of the planet in terms of the mass of the Earth? So I'll let you think about that for a minute or so. So here, G on Earth is big G, mass of the Earth over radius of the square. So we know that G on Earth equals G of the planet. So that's G times mass of the planet over radius of the planet squared. We know the planet's radius is 3 times that of Earth. So big G times mass of the Earth over radius of the Earth squared equals big G times mass of the planet over 3 times the radius of the Earth squared. So that's 9 times the radius of the Earth squared down there. Now we can cancel some things. Radius of the Earth squared, big G, and big G cancel out. And so we get mass of the Earth is mass of the planet over 9. So the mass of the planet is 9 times the mass of the Earth. Any questions about gravity? So another thing that's associated with gravity is buoyancy. So buoyancy is the fact that if you have something in a fluid, any object in a fluid has an upward force from being wholly or partially immersed in the fluid. And Archimedes' principle says that an object immersed in fluid will experience a buoyant force upward equal to the weight of the volume of the fluid it displaces. And both liquids and gases are considered fluid. So what this means is that if something is more dense than a fluid, it sinks. And if it is less dense than a fluid, it floats. So as an example, here, this is water with a density of about 1 gram per cubic centimeter. This is aluminum. It is more dense than that. It's about 2 and a bit. It's about 2.6 grams per cubic centimeter, I believe. We'll see, it sinks. Don't know if I have anything lying around that's less dense, but I think this might be. So this is a hollow plastic thing. I believe it is less dense than the water. As you can see, it floats. Its density is less than 1 gram per cubic centimeter. So the buoyant force depends on the weight of the fluid displaced, and the weight of the fluid displaced depends on the density of the fluid and the volume that gets displaced. So salt water is more dense than fresh water. Therefore, if you go float in salt water, you float higher. If you float in extremely salty water, you'll float even higher. So if you ever go to like a salt sea, like the Dead Sea, you end up floating really high in the water and it feels very strange. Or some other salt seas that are out there. I don't know. So you hope you float higher in salt water because you can displace less salt water to equal your weight. And if you're dealing with something like a very dense fluid, like mercury, for example, you can drop an anvil on mercury and it will float. There are some videos out there online if you want to see that. It's kind of hilarious to see. So ships float because their average density is less than the water they would displace. So most ships are made of steel, which is more dense than water, but they have a lot of air in them. So that makes them less dense than the water they displace. Oil floats on water since oil is less dense than water. Cream floats on milk since cream is less dense than milk. And by taking in or pumping out water, submarines can change their mass, so change their average density and vary their buoyancy. That's how submarines can go up and down. They pump in or pump out water to change their density. And I'm going to stop there for today. We'll go over this again when we get back, but we're going to have our quiz. So let me stop sharing.